Let's wait for a couple more minutes for people to join. Am I audible? And if you guys are able to see the slides. Okay, let's start the session. Yeah, so this is a introductory class for VLSI verification. Basically, we will be covering what is meant by VLSI, what are the different aspects of VLSI verification, how things have evolved, brief description about that, and what would we be basically learning in this course and how it would help your career. So good evening, everyone. So my name is Ravi. So I have been in industry for about more than 9 years. So working in various domain in starting from verification to modeling architecture and different things. So I would be the host for the day. So basically the term VLSI indicates that it is very large scale integrated circuit. Very fancy name. I think we will go with the following covering the following things. We'll be doing a brief introduction to VLSI, different VLSI aspects of the VLSI flow that are there, how we arrive from thinking to actually the silicon or the processing, where exactly it is used, what is an SOC, course flow, hardware description language, which is called HDL, and why there is a need for verification as such. So coming to the part, what is VLSI? VLSI abbreviation stands for very large scale integrated circuit. So in this process, you actually create the integrated circuit by combining thousands of transistors into a single chip. What exactly is a transistor and what do you make out of transistors? So basically, transistor is a physical method by which you actually make the gates, where you command things to be done, whether you want to set it to 1 or 0 or create a logic on top of that. So these are the, so transistor you can take as a fundamental element, like a cell in our body, like how our body constitute of cell. Transistor is the primary ingredient or the constituent of all the VLSI chip that we have. So VLSI industry began somewhere around 1970s when these complex semiconductors and communication technologies were being developed. Previous to that, there were gates, logic gates that were there, and they were used in industries also for doing some of the automation stuff, but their size was pretty much huge. With the advent of some of them were mechanical switches that they were being used at some point of time, but as the technology developed and we had the transistors, that's where the industry changed forever. Even just give you an example, where exactly do you see VLSI industries work? Where you can see, I would say you would see everywhere, right from the laptop from which you are hearing my voice or viewing the screen to your phone screen where some of your friends might be messaging you on WhatsApp, or the vehicles that you use, like from the cars with your own bikes that you have, or any electronic gadget like any mobile phone or playing even toys, any enhancement from your Wi-Fi router from which you are communicating, it's very hard to say where you're not using. Even you just go to a room, I would be really surprised if you don't have any VLSI or an electronic device that is there. So, so these are different things that are there, and at point of time, the most complex thing that would be coming up with the VLSI could design what sort of a microprocessor or a CPU system. And now things are like way beyond that. Like CPU used to be the most complex thing that would have been developed, and there are process of Intel and AMD or different companies are a risk processor for your mobile phone that being developed. But things in the current scenario are really different, and how they have progressed at an unimaginable rate at which the technology has progressed. So that's what VLSI is about. And yeah, so being a high demand industry and high so there is a huge demand in terms of consumer goods that are produced by VLSI. Also, even in terms of job opportunities or making a career in VLSI industry is fancy, both in terms of the technical challenges which you aspire, also with respect to the pay that you get. So in either ways, it's a good industry, and it would stand straight. Someone if you're looking for a VLSI enter the VLSI industry after your college grad or after working in some other domain. So it's a welcome to you guys. It's a good thing, and I would say you don't regret your decision. Only thing is you might have some hurdles in crossing and understanding and making yourself equipped with the right tools. So yeah, let's come to Moore's law. So what has led to such an development of VLSI industry? So have you heard of this name? Anyone on the bridge or the call? Who is Moore? Gordon Moore. So Gordon Moore is one of the founding member of Intel and a technologist. So what he stated was, for every 2 years, the amount of transistor that would fit into a space will double. And that has been really true, looking at the trend that is there, and the cost of the computers will come down. So do you guys agree that it is really the case or not? I think you might have observed in various cases, like for example, in your mobile phones or processor. Just to say, like for example, what NASA was having in 1980s or 1990s duration, the kind of computer or the electronic or the VLSI was present in the NASA, the rocket sending organization, which is supposed to be the most advanced thing, is nothing when compared to the mobile phones which you are operating in the current day. So that is what the thing. So once at a point of time, the technology which was available only for sending rockets into space and the utmost biggest scientist now is available to everyone, every nook and corner, much better version of that. So that's how things have progressed. Yeah, and we know the current generation, the technology node of transistor that is running is like 4 and 5 nanometer technology that is running. If you have some Qualcomm Snapdragon chips and this thing, that's where you would see things, how your chips are placed. So yeah, so coming to VLSI flow. So what is a flow? How do you make this chip? How and where does it start, and what is the process that is organized in the industry in doing so, is something that we will try to understand in a superficial or overview way in this slide. So basically, there are two parts that are defined. One is called front end, another is back end. Front end is the one, the actual crux and the core of it. Back end is the one that actually physically implements it. So I would say you consider this as an analogy of building a house. So front end would be the planning part, how things should look, how the room space is there. You architect the design. You come with a specification, like what is the area of the space that you have, how many bedrooms you want, how many bathrooms you want, where should be the kitchen. You should be big, and it depends. Like what is the kind of thing that you are developing. It's not necessary like everyone has a similar taste. Like how houses are different, different chips are different, and it meets different specification. Some of them are advantages at one edge and have a little bit slower sluggishness at the other edge. It all depends upon what you actually care for or look for. I think these kind of thing you might already be doing. If someone is tech savvy while buying a phone will definitely check for what is the processor speed that it is running, what is the memory support that it has, what is the size of RAM that your phone has, what is the kind of camera that you are designing. So everyone has their own specification. Depending upon that, they choose the products. Sometimes money is a constraint. Sometimes you need a very good camera. Sometimes you need a very good internet modem that your phone connects. So depends upon different things. Based upon that, you come to the architectural design of that. Like you come to a design of that. Then you space the logical aspects of it, where what things are placed, how do they function. Now you know the blocks, and you know what is the aspect of that. How do you make them do with the logic gates? And functional logic is what you create. And once you do that, then it boils down to the circuit design. So what circuit do you use, which technology node you use, and how the things are there. And at this point of time, the diversification start, where you actually come to the physical design aspect. Till the point of time, everything is in simulation, everything is in the air or in the software, or things in the discussion, but the actual physical implementation is what puts you together and comes as a small chip there. So you have the silicon, and you try to make the transistors, and you make the logic gates blocks there and connect that, and you see if the timing of that is met, how you align the clocks for that, how do you fabricate that, which technology you use, which company you go for fabrication. So all these are different, and then comes to packing and testing. So these are the different. And in the physical design, you do the partitioning. So you want to put it in a very small space, like how our real estate cost is high. Same is with respect to the ASIC cost. This is a high-end technology. So even though it is in microns and barely visible to your naked eye, the space is a very important constraint there. So with an available space for every nano inch of space, you have to spend some millions of dollars for it to go to the fab level. So that's how important it is. So you partition it, you floor plan it, how do you connect the different block, you do the placement, and then you do the clock tree synthesis and signal routing and time enclosure. This part you can consider like you design the house, you plan what the things would be there, what color your wall would be there, what furnitures are placed at this point of time. But what do you actually need to build a house? That is the back end part. You need brick, mortar, cement, place good amount of iron, and these are the things that are actually required in the ground level. So that is the physical backend that is there. So depending upon the interest in which people seek, so you can opt for different domains in that. You can be a designer where you can be an architect, you can be speaking at the customer front where you talk and actually get the specification. Hey, market needs this kind of one. More people, young guys are interested in gaming, that's where you wanted to go. Or more better camera is there, so the AA processor is required, so that more beautification of the images are required, is the necessity of the day. So something of this kind, depending upon different fields you can have. Or you can be an actual designer, or you can be a physical designer where you do all the placement, routing, or clock synthesis, or one of them. Or you can be at the back end, or you can do the validation at the back end. Once the silicon come, how do you do that? and different checkings that are there. So this is here in a way it shows in the diagrammatical form, like how do you analyze in this thing to writing code to getting the circuit to actually connecting them, placing them, doing different tests, getting into the silicon fab, and then actually doing the packaging and getting the final chip. So functional verification is a process that we establish for the front end design. So what you actually try to do is here, when the functional logic and these things are made, you try to actually verify that what is the expected output of that, and if it is coming as per expectation or not. So how do you do that? So you use either a language, uh, I mean, verification language, VHDL, verification hardware description language called system verilog, or a wrappers and a well sorted methodological form of unified verification methodology, so that you can use it again and again. So what are the things that we cover in the course flow? So these basic concepts are divided into 4 phases. One is the digital electronic part, where you understand the fundamentals of the things that are being done, like your if you're from electronic background, most of the things you would have known, like what is the Boolean expression, how digital things are expressed, what are the gates, how do you do simplify that, what are the different laws binding them, and these are the things that you would be studying. Next part is the verilog, which is the HDL, in which you actually write and code the hardware, and this is what will actually go and get synthesized and come as a physical chip when backend people work on that. Third thing is the system verilog, which is an similar structure to Verilog. It's a verification HDL, and it is used to verify whatever design that you have written there, using different test cases, creating scenarios and stuff. On top of that, if you want to structure the system Verilog code or verification thing, there is a thing called unified verification methodology, UVM, which is universally accepted form. There earlier used to be OVM and other things. Now UM is in place. If you go to different industry stand, why do you actually use it? It's not like you write everything from the scratch. So industry makes sure that you put least of the effort, or effort already put is made to the best utilization. So here we come about the digital electronics. So digital electronics are like we described. So all the different types of gates that we have, how do you make them, how do they function, what is the output and input of that, how do you group them, how to create a logic for that. So in the primary aspect that we will be covering is the combinational circuits and the sequential circuit. Combinational circuit are the circuit where the current output will be depending upon the current input and a logical function applied to them, and they doesn't depend upon the previous input or doesn't hold any memories as such. Sequential circuits are circuit which have a combination circuit and a memory element added to it. So output not only depends upon the input but also the past output. In that way, you're adding a element of memory to it and doing that. Like for example, in game or something, some action is preceded by the previous action which is stored in the memory and then comes back. So let's see what hardware description language is. So hardware description language is a specialized computer language that is used to describe the structure and behavior of circuit, commonly called as digital circuit. So generally what you do is you allow automatic analysis and simulation of electronic circuit. Use that you synthesize the HDL, create a netlist and physical component out of it, which can be placed and routed in the back end, and that's what makes the integrated circuit. So like how you have a C program, HDL is a hardware description language where you try to write the hardware. The difference between C and here is C, you have the logic, you just think about what you intend to do. Here in the hardware description language called Verilog, what you try to do is not only you check the intent, but also see how it get realized physically and how that physical connections come. Because ultimately, whatever you write as a code has some physical form. Unlike software, it is finally going into the binary format as executable, which the processor will come and execute. So there are two different types of Verilog description, hardware description language called VHDL and Verilog. VHDL is mostly used for the academic purposes or writing into FPGA thing. It has its own advantage, but most of the industry, everything has adopted to Verilog. And you can write at three different levels of language. One is data flow level, behavior level, structure level. Data flow level is what you write in intervey in with an intent. You know how the data is flowing. Behavior level is where you write it something like a C program, writing it in a C program, some writing functions to it, or writing it in assembly language. Structural is like writing things in assembly language where you should know what physical elements or gates that you're using, and then try to use those blocks and create the logic. As the designs go complex and complex, we mostly use data flow and behavioral model. Yeah, though there some places where we might be using structural model as well. So why do we need a HDL? Why can't we program everything in terms of gate itself? Because the complexity of things is increasing. It's very hard to program everything at the structural level. Just this is P4 processor. I think nothing of something which you would have seen or you should have been really kids while this has come. Like it's like 10 years back. So it itself has 40 million transistors and it is running at 1.5 gigahertz, and current state of process that are there are like 5 to 10 times or much more advanced than that. Even if I say processor which are like 100 times advanced than these are in preparation, yeah, it would be definitely a valid statement. So everything cannot be done at gate level, and so you go for HDL where you have a level of abstraction which you make use of it and then go for it. And based upon that, you have computer aided design tool in the design process which actually convert whatever the HDL that you have written, synthesize into hardware blocks or the logic gates at whatever nodes or the technology nodes that it is being used. So this is the process that you show. So you write something of a Verilog code here, and your computer aided design or the CAD tool convert them into the logic gates, and then you actually combine, write the timing information so that you get the reliable output on a target technology. And this is what your actual design on silicon would come to when it goes to the fab. So yeah, as I was describing, Verilog is the industry standard. It all starts with a module and end with the end module. You declare the module name and have a ports in it, input output ports, and the operation or the procedures that are captured there. So that's what it is used for. Verilog is used for both design as well as verification, but using Verilog for verification is not very applicable because most of the things are not synthesized. So then came an add-on called VHDL is something as described, is used for FPGAs or in academic purposes. If you see the difference between Verilog and VHDL, these are the difference. So it's used for modeling an electronic circuit. These are used for digital and mixed signal designs where both analog and these things are there, especially in applications of FPGAs or in academic purposes used. This is based on C, this is based upon Pascal or something. It is case sensitive. VHDL is not case sensitive. It's newer language. It's older compared to Verilog. It's less complex and more complex. So frankly speaking, Verilog in terms of language is much, much, much simpler than even C language. But thinking in terms of Verilog, going and seeing how that design will actually synthesize to and get the hardware block is something where the designers have to put in their effort. And what is test bench? Now you know the design. How do you ensure that it is working correctly or not? Even when you go to a mobile shop to buy a thing, first thing you try to do is you test for camera, you test for the sound and these things. So how do you test design? And when you're making such an effort and trying to produce millions and millions of chips all together, it makes sense that your testing system is all robust and everything is taken care that there is no error at all. So the precision in the design and verification flow are like very hard bound and time limited to market because many competitors are there. That's where the need for verification arises and how you test the design. So you try to simulate, try to check the use case of the design in some aspect and see how the design is behaving is as per intent or not, as per spec or not, and then you confirm the things like whether everything is as expected, or if you give some undeterministic condition how the design behaves. So there are different aspects to it which you'll be testing using a test bench. So basically test bench is the thing that you use it to actually verify and validate the design. So what is ASIC and FPGA? What are the difference between these two is something which you might touch upon. So ASIC is the application specific integrated circuit, FPGA field programmable gate array. Some of you might have already done some part of Verilog coding in your academics, where you might have burnt your code into FPGA LUTs and then try to validate the design. ASIC is a chip that actually comes manufactured. Once it is designed, it's designed for sure. It is for a specific purpose, you just do it. Whereas field programmable gate array is something where you can configure it each and every time differently, try to use it. Though these are for testing purpose. Even at the industry, before actually manufacturing ASIC, you test the design in the FPGA, try to correct all the bugs because it's faster than the simulation. Not software is not running, actual hardware is there. You configure those blocks and then you try to program and check it. So we'll be also checking the FPGA architecture, how they are made and different stuff. And we will be studying system Verilog based verification and touch upon some of the aspects of UM as well. So main problem of verification is it's time to market. You say you have a small design, and if you can test it in some 5 years alone, then it's good. Yeah, I don't say it cannot be done at all, even the most complex thing. But what if after 5 years many people have advanced and released better things than you? So time to market where it comes, and that's where you try to establish methodologies, common functionalities, reusable, whatever the test bench that you have used to verify a particular design, if you can port it and use it to some other design. So what are the different aspects that would be covered is something that you would be studying. And yeah, here comes the UVM part. So if you see something that is specified here as a DUT, this is a design under test. You actually communicate, you pass on the inputs and take the output. And there are different layers of the unified verification methodology. One, you apply the clock and these things. At above level, you have the driver that provide the input, which will actually burn down to the digital signals connecting to the port of the DUTs. And you have a BFM, which is a bus functional model or a C model, where you also drive the input and check what is the outcome. Then you validate your design's outcome and try to compare it if you are seeing expected results or not. That's what it's going to come. Apart from that, there is a mailbox which communicate, and there is generator which actually generate the test, and test can be written in terms of transaction. And you also check for the coverage, like how much of the design is tested and how to do, and you group different blocks of that and try to do that. So everything is placed in different layers so that people can work in peace at a single layer and try to fix it. If they want to make any generic change, they make it a different layer so that these things can be reusable at different points of time. And let's see what an SoC looks like. So this is a system on chip, maybe what your mobile processor is using. It has a CPU, it has an interconnect which communicates to different things. Either it's internal memory or a bootloader program. Once you start off the thing, once you reset or restart your mobile, it shows up the colors, and so that's the bootloader program. So it's not the actual CPU running. That's why it takes time with some weird music and DFT, design for testability. Like you make the design, and after the silicon comes also, you have some hacks where you can actually test the design through the gates. And other things are there. You have a DSP transmitter, like for example, if you want to process the audio and other things, you make use of the DSP transmitter and receivers. And there will be things like analog to digital converter or digital to analog converters where you actually transmit the system. Like what I'm speaking is an analog signal, and that gets converted to digital signal using various analog blocks, and then you apply different DSP filters on top of that so that you hear and process things in a much clear fashion. So, and other things like on chip protocols are present. Like if you want to communicate between two different IPs or two different chips within the same die where they are sitting together, you use something called as AMBA protocol, which was made by ARM company. So that would be it would ensure communication between two different blocks. A standard protocol is established. How do you handshake? How if you want some information, what is the procedure to ask that? Apart from that, there are different kinds of peripheral connections that are there, like USB connection, where I think everyone should be aware of the latest USB-C, whether you charge it or transfer different data or connect different devices or storage for memory, use different USB devices, or PCIe communication that you use if you are using are a gamer, or so connecting your graphic card to memory. These are the different things that you would be using. So why do we need a need for verification? One is time to market that we have seen, and we need to know how our design works. And yeah, as we have seen design, we do it using Verilog, and for verification, you use system Verilog and UVM flow put together. So yeah, that's all, or pretty much about the quick introduction that we have for the thing. Yeah, if you guys have any questions, yeah, I would take some of them with respect to the course or VLSI in general.
Hello.
Hello.
Hello. Good evening, sir.
Yeah, good evening.
Yeah. Sir,
Sorry, your voice is not audible.
yeah, we are willing to take the course, sir. So to become a verification, how do you categorize the students? How do you push the students to the different means design field and verification field?
So it see it's so it is up to you how do you take up the thing. Like for example, in this course you would be actually learning aspects of design as well, because to actually verify the design we need to know how the design is made as well, right? Without
Yes.
that you would not be able to verify the design. So you'll be covering that. But if you want to go into design field or verification field, that is something you have to choose and work on it. So that is like if you want to go to the back end, maybe attend different sessions of the I mean design course as well as the physical design course as well. So based upon that you can take that.
It means that means you are going to cover the backend syllabus also.
Sorry.
Is it right? That
Can
means you are going to cover in this course backend subject also.
no. So backend won't be covered in this course. So the part what we'll be covering in the course is shown here. So these are the parts. So digital electronics, Verilog, design aspects, system Verilog, and UVM.
Yeah, that
And
means you are
yeah,
for verification. Yes, sir.
yes. So this is for verification. This primary for ASIC verification itself. And these are the courses that we'll be covering here. Any other questions? Sorry, I cannot hear you guys.
Yes. Hello.
Yeah.
Someone is speaking. Hello.
Can you mute yourself or yeah.
Yeah. Hello. Hello,
Yeah.
sir. In this you're going to talk about that what do you call this model sim and cluster sim and EDA playground.
Sorry. Yeah, right. So basically here we don't use exactly model sim. We'll be using VCS tools, which would be on similar lines. Once you learn one thing, other thing is just like riding a different kind of bike. Like it's not like if you know how to ride Hero Honda, you cannot
Okay.
ride
Different kind of
other bike, right? So once you know how to ride a bike, it's mostly similar. You just have to know whether it's front gear or back gear and some of the things where how. So it's
So is there any chance for paying EMI ways, sir?
sorry.
So is there any way to pay the money in EMI way? Means monthly installment.
Actually, I think those details you can check with the admin once. I am not
Okay.
sure about that. You can talk to the HR or the admin of the institution. So any course related queries or career things, maybe I would be able to help you. So for the other things, you can contact the HR who actually directed you to the session, right? For that.
Yes. So I have one more question, sir. And
Sure.
uh, to master to learn this verification course, to
Huh.
shall I need to learn C language and Java? I
Not
don't know. And
not necessarily required. If you know a bit of that, it would be easy for you to understand the nuances. But it's not compulsory that you should know C and Java. Java is not at all required. For some of the verification, you use the C language. Like for doing the SOC
classes,
level verification, you
functions
might require C language. So it depends where you want to go in
in
verification.
functional coverage, sir. In functional coverage.
Not not coverage in writing the test itself. If you are doing SOC level verification, then you would actually be using C language.
Hello.
If you are actually doing in terms of Verilog, I mean, if you are actually doing IP verification, then you'll using System Verilog and UVM plus. UVM will be there anyway in either cases, yeah. But whether you use C or System Verilog will actually vary there. But in this course, we will not be covering C aspects as such, but we will be covering System Verilog itself.
Hello.
Yeah.
That's all.
Hello.
Yeah.
Hello. Which hello? Which
Uh,
hello? Which
hello,
tool we're going to use?
sorry.
Which kind of tool we are going to use?
For see, so HDL, what you will be learning to use is Verilog for design, System Verilog for verification, and some aspects of UVM will be covered.
No,
And
I
tools
mean
that you are going to use for actually doing the EDA tools would be VCS tool.
which tool, which software we are going to use?
VCS,
VCS.
Synopsys tools.
Synopsys tool. Okay.
Any more questions?
Hello. Hello.
Hello, guys. If you are
Hello.
speaking on the
I'm
call,
Rahul.
maybe you
Hello.
can mute yourself.
Hello. Can you hear me?
Yeah, just one of you speak and rest of the guys can mute. Yeah, I can hear you.
Sir, hello.
Yeah.
Sir, without having knowledge in C language,
Huh.
so no, being good at system very luck, is it possible to get is it possible to achieve the job in this verification field, sir?
Yeah, it is possible. It is quite possible. But you should learn system Verilog.
Yes.
If not C. If you say I cannot learn system Verilog also, then it is not possible. You should learn
No, no,
something.
no, yes, I'm asking. No, I'm not sounded to C language. If I learn system very luck, that is enough for to achieve the no, job in this.
Yes.
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 Okay. 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 Thank you, sir.
Hello,
Okay.
can you hear me?
Yes.
This is Rahul. Actually, right now I wanted to develop a product based by using this FPGA of the Altera.
Okay.
So yes, so actually, how can you help me on that actually? So because right now I'm using that VHDL language to interface with all the peripherals and
Okay.
creating
లేపే
yeah and creating all the
బియ్యాన్ని లేపు
hello.
Yeah. Yeah.
Yeah. So all the peripherals I have interfaced using VHDL, but right now I'm facing problem with this memory devices and all the devices which I have to like storage. I am not able to use VHDL as effectively as we can do in SOC, which is also provided in the FPGA. Like I'm using Cyclone 4. So what do
Okay.
you suggest? What do you suggest for developing the product? What do we use actually? Is this
See,
VHDL is good practice or
VHDL will help you only in academic. In your
okay?
college projects, it will help you to do
Yes,
that.
yes,
Okay.
yes,
But how it will help you once you come to the industry is you have to learn Verilog and code it. Only thing is, if you already have the VHDL basics, it will not take much time to transition into Verilog and system Verilog. That's how it is good. But having said that, there are still some very few companies which use VHDL also, which would be very rare to find as such. But as such, again, to your specific project, taking up the VHDL, I think it would be difficult because 95% of the industry adopts Verilog only. So
okay.
that is the reason we have chosen to go with the Verilog and Verilog as the thing. Like 90% of the code, or even more than that, I might be very pessimistic. 98% you can say in all of the industry, which is actually producing successful chip, will be
Okay.
using Verilog code itself most of the cases. So in
So
that case,
actually there is another option that I was asking about that SOC creation and writing all the program in C. So how is that useful to develop a product?
so I didn't get your question there.
Actually, we can program in three ways, like you said, Verilog and VHDL, and then there is the C. So we can create a CPU on Altera devices, and we can program the device in C. We can write all our algorithms and routines in C,
Right.
and yeah. So I was asking that can it is used for developing a product by using
You
C?
see, see if you are developing a product, if you are anyway thinking to make a product, you can
Yes.
already get a processor that is there, right? What you want. On that,
Yes.
you can program and get it, and then you can make your own PCB device and develop a product.
Yeah,
So
yeah. Actually, there is actually limitation. So I could not use my microcontroller and CPUs like normal processors. I had to jump on FPGA because of some basic requirement in this field, printing field. So that's why I had to switch on FPGA, and that's why I was asking that what is the use of C and creating that SOC like CPU creating
why do
CPU.
you need a SoC for? In that case, you can directly go for already existing processor that will serve your need, right? Existing in market also, Atmel processors are there, microcontrollers are there, depending upon the use case that you are trying to do. I'm not really sure about that.
Yeah,
That
actually, we are developing printer, which is CIJ printers, continuous engine printers, and all the industry-based companies are using FPGA only. Because in start, I tried to use STM32 based controllers, which are ARM Cortex, but they couldn't do the job actually because there are various voltage levels and all that timing and other characteristics which are needed.
so then in that case you can build through your FPGA itself, right? The hardware
Yes,
that you want to develop, then you have to go ahead
yes,
and develop in VHDL only, and then only you can do the programming. Or you can
okay,
directly build a hard-coded thing for your application, maybe add some small soft logic to it.
okay. Okay, that's why actually I wanted to learn this VSDL Verilog and all that. But basic requirement was that I had to develop a product on that.
Daddy good ending at
So in that, yeah,
Amazing.
I understand your concern. So basically, you wanted to learn Verilog so that you can make the product that
Yes,
suits
yes,
your
yes.
requirement.
That's why, because when we use a CPU, then there is also it becomes like a controller, and then we have to go like that. And in this VSDL, we can create concurrent processes,
Exactly,
and yes,
exactly.
and that is more fast than building a CPU, and
Right.
again on that using
See,
micro OS and all that.
what I would suggest for you, because you already have clarity on what you want to achieve,
Yes,
and you are saying that you already have a FPGA board, and your
yes.
FPGA board doesn't support Verilog code, right? It supports only VHDL, or you know VHDL.
I know VSDL, but it supports both VSDL and Verilog, and also C.
Okay, then I
Yeah.
would say if you already are familiar with VHDL, then go ahead and do it, because that
Okay.
will give you an advantage, because your intention is to make the product on FPGA, right? Go ahead and
Yes.
do it
Yes.
in that way.
Yes.
But
Yes.
having said that, if you are saying that VHDL also, I am not like 90% sure to learn, or I know only 10 or 20% of VHDL, then I would
Okay.
say take time to learn Verilog and do it. Because if you once you learn Verilog, the resources that are available for
Yes.
you, if you are stuck in Verilog, are much more. You won't be stuck much. But if you say, if you are already very much like, I know 90% of VHDL and it's very comfortable to me, then
Yes. Yes. Yeah.
I would
Yeah.
say go ahead and do in VHDL only. Whatever problems will come, you
Yeah.
try to sort it out in the way. But very less resources will be available. Only your college professors might be able to help you with that.
No,
Not
this is out of reach of all the
but
professors also, because I wanted to consult my friends also, which are in Intel, regarding that, this so they can help me, but there is no one which is developing right now product on FPGA. Very less people is here, so that's another problem. Actually,
yeah,
yeah,
those are the two things. You can
yeah.
choose one of them to do that.
Yes, and the other thing is that if we are using VSDL, then this where like if I'm using like communication protocols, like I'm connecting any devices on UART or something like that, then there is the problem of this data taking into the buffer, and how to process the data, and parsing of the data. That is the problem I'm facing right now. So
So
can we do it? Yeah.
so what is the question there?
So can we do it easily in Verilog? Like processing the data from the UART, and performing different tasks on that.
It depends. Everything will have its own challenges. But
Yes.
having said that, Verilog you'll have enough resources. You will be easily able to do it.
Okay.
So if you don't know to interface it anyhow in Verilog and VHDL,
Yes.
if you try it in Verilog, if you are able to do it in 10 days, the same thing
Yes.
if you try it in VHDL, it might take 20 days or 1 month.
Okay.
Not because of your capability, but because debugging or resources. If you find, suppose you find an error in VHDL,
Yes.
to solve that, not many things would be there. If you just search some error in Verilog, you'll be easily able to figure out where that is
Yes.
coming and
Yes.
how to solve a
That
problem.
yes. That
And
problem I'm facing right now, because
so
I'm
since
using
you're
signal tap.
developing a problem, you have to keep time factor into account, and you have to take those aspects into account and then make judicious decision in what direction you want to go.
Yes. Yes. That's why I was asking actually, because I'm using signal tap logic analyzer for checking all the data which are when my system runs for checking and performing tasks. So that is another problem there. But I'm convinced that you can also help me in that.
But see, I would not be able to help totally because this course doesn't cover that.
Okay.
And VHDL, I really don't have idea about, frankly speaking. So
Okay.
that's the main problem. So like, and that's what you can only find people knowing VHDL well only as college professors, if they are existing.
Okay.
that's only you can try to seek their help there.
Okay. Sure. Yeah. But thank you.
Okay. Okay. See you guys. All the best. Have a nice weekend. Yeah. I think we are pretty much done here.
Yes. Yes. Thank you.